Hey guys, welcome. My name is Jonathan Knapp and I'm a geologist. And my job at Hitachi is to be new business development for green energy, mining, and related technologies. But I also am the project manager for our AMICS software that's developed in collaboration with Bruker. So I've been part of the AMICS team since 2018. Today, this is our launch of our AMICS 3.3.3 product. And so this is kind of exciting, and I get to show you some of the new things we've done. And I'm even going to give you a sneak peek of something that's going to be released in our 3.4 release in October. So, and this was a feature that we're going to show today that was requested by the USGS. And so I think that that's kind of an exciting thing to show. So today, my background is, my PhD is in geology. I'm a sedimentologist by training. But I have my examples today. I only have a few oil and gas examples, so you're all welcome for not boring you to death with porosity. But we're going to get into some really cool stuff today about what we can do with automated materials characterization on the Hitachi SEMs. So just to start off, I want to say we're part of Hitachi, which is a gigantic company based in Japan. And Hitachi has a long history in mining, over 110 years. It was actually founded as the machine shop at a mine in Hitachi, Japan, which is pretty cool. But we've been part of the science community for 76 years here at Hitachi High-Tech, and we really specialize in industrial high throughput scientific imaging and data analytics. And so we're very excited that this product continues that tradition and has a strong foundation in mining, but has lots of other applications as well. So AMICS itself, AMICS stands for Automated or Advanced Material Identification and Characterization System. It's a fourth generation automated mineralogy system. So anyone here, show of hands, who is familiar with automated mineralogy? Great, okay. So this would be the original automated mineralogy systems were QuemSem and QuemScan, followed by MLA, and now we have a new generation of technology out there, and AMICS is part of that fourth generation automated mineralogy technology. And it's developed really in collaboration with Bruker Nanoanalytics, and the system itself has been under development since 2012. And so we really want to acknowledge our history that, Dr. Ying Gu is the founder of this company, and I took over for Ying in 2018. Unfortunately, Ying passed of cancer, but we really do feel like we're carrying on his legacy. And a lot of the coolest stuff in AMICS is what we like to call Ying things. And so going from a relatively small team, we now have a large team, working on AMICS as well as working on automation across Hitachi. So today I'm here launching AMICS 3.3, and I just wanted to talk about a few of the quick features here, and then we'll dive into it. But I just wanted to, the point here is one of the biggest things that we've introduced here is project management, and we're always advancing, and we try to have a cadence of releases, about 2 releases a year. And the most important thing is that this software is really driven by the community, by you. And so what we work on is really driven by our users. What do our users request? And what types of features are needed to challenge the most important challenges and workflows. And so we do a lot of specific workflow development. So what is the philosophy of AMICS, the core of AMICS? The first is that we're a tool and not a method. So we're applying methods. Many of those methods are developed by our users, but we don't specify an AMICS method. And instead what we want to give you is the maximum amount of flexibility to measure how you want to measure. So every measurement mode that we have in AMICS has come from the community. It's been a request from the community that we've implemented. And we try to give the maximum amount of flexibility to build those recipes for data classification and data collection. We really are trying, like the core of AMICS is try to discriminate close phases. This is, advanced material identification. So our job here is to use multimodal data sets to identify phases and then translate those phases into data, right? We're designed for high throughput. This is a high throughput industrial system. It comes with holders, it comes with automation designed around it. And then we're really focused on open source and cloud platforms. So one of the things that we're committed to here is that our file format is open source. We're developing a new open source file format. And then we're working very closely with Hitachi's cloud service providers to be able to enable your workflows in the cloud. So what is AMICS? What does AMICS do? The first is it automates data collection, right? So these are automation routines, and you can see kind of what a typical sample holder looks like. The whole point is to put many samples in the system at once, design your data collection routine, and push a button and walk away from the SEM. And this is collecting large area mapping and collecting EDS data and imagery data at the same time. It then has data reduction and classification. So the point is to take that EDS data and that image data and use those together to identify the phases that are in your sample. And finally, we have the quantification and of the image data. So we want to translate that image and EDS data into numbers. Modal data, understanding its relative abundance, plus all of the textural data, things like particles and grains. So this is a system. So it comes as a system fully integrated, and we spend most of our development time getting all of these various components to work together in a fast and secure way. We're really focused on making sure that we have a high throughput system. So that means that it has to meet industrial requirements for uptime and measurement. And what parts of the system, what brings it together and makes it a system? First is that we have the things in the chamber, the sample holder, the standards. So that means BSE standards and EDS standards so that we can apply quantification to both our images and our EDS spectra. We have the detectors, and those detectors, we use Bruker XFlash Generation 7 detectors on our systems with 1 million throughput count in the electronics. We have, and those are optimized for data collection at our analytical distance because we need to optimize our imagery and our EDS. The column, as well as having the software and special electronics. So this is a fully integrated system. So let's talk about data collection. First, we use the Bruker XFlash Gen 7 detectors. This is developed in collaboration with Bruker. And so we really are excited about the Gen 7 for a couple of reasons. One of the most important is that the slimline technology allows us to get a 60 millimeter EDS as close as possible to that sample, which maximizes our count throughput, so we can get the type of counts and the type of that we would normally get with a larger area detector with still having the resolution that we need for matching and have better matching. We also have the up to 1 million valid count throughput, which allows us to collect data much, much faster. And so we're really focused on speed here. We want to collect enough spectra in each point to be able to do a high quality match or to do at least the start of a quantification. We can talk about quantification a little bit later, right? And so this is why we really recommend a dual detector system that also reduces the shadowing and maximizes your uptime. One of the things we really like about the Gen 7 detectors here as well is for maximized uptime is that we have a field replaceable silicon drift detector so that the whole EDS doesn't have to go back to the factory to replace the EDS detector if there's anything that happens. Or we also have to remember that these applications are probably one of the most photon intensive applications that we do in electron microscopy. And so silica will eventually degrade over time if you pound it with 1 million, 3 million input counts all the time. So we want to make sure that we've got that ability to continuously refresh that silica. We also are available on almost any SEM that Hitachi provides. And so the system can be fully integrated into everything from the Flex M1000, which is a compact SEM. These are being deployed, for instance, on oil wells for drilling all the time, all the way up to our SU7000 system is kind of a popular system for research applications. So what is the core of what AMICS is doing? So we have many measurement modes, but I wanted to talk about one of them right here with a quick example, and that's image segmentation. So we're applying an image segmentation to the backscatter electron image and then taking a representative point. So the point gets taken inside the segment, and then that is used to represent the segment. This is one of our mapping modes. But we have many mapping modes. Forgive my cartoon. I'm going to make a better cartoon, but it's just in process. So we have segmentation mapping mode, which I'm just going to walk over here. We have the segmentation mapping mode. We have hypermap mapping mode, which is going to be over the entire system. We have matrix mapping mode, which subtracts the background and then puts points at a user-specified spacing. We have rare phase search. This is the cartoon that you guys are allowed to make fun of. PowerPoint special. And then we have triggers. So what we can do is we can trigger different mapping modes based on criteria within it. So I'll go through each of those. So matrix mapping mode is, this is kind of my go-to, right? I work with a lot of fine grain rocks, and so this is the most appropriate measurement mode for fine grain rocks. So we move the stage, then it collects an image over the image, then it subtracts the background, and it's the user can specify what the background is. So a lot of what I'm doing, I've got a relatively narrow range of background. Segmentation and points placement. So essentially what we're doing there is we're pulling out the grains and then placing points in a matrix around the entire grain. Then there's EDS data collection. It creates a classification map, and then it moves on to the next frame. And so it's a frame-by-frame mapping over the entire user-specified area. Segmentation mapping is very similar, with the difference that this is where we actually have segmentation of the particle itself, and the point place is placed in each of the BSE areas. So this is a faster way to map, and it can also result in if you have large enough crystals that they can be resolved by the BSE, it results in a map where the crystal boundaries will be following, or area boundaries will follow the BSE, so they can be at the resolution of the BSE instead of the resolution of the pixel spacing. So triggers, you start with segmentation mode, and then what you can do is you can then place a grid of points inside each pixel if it meets specific criteria. You can also just do it to all of them, but so the criteria that we have right now implemented are what phase has been identified. So you can say, every time you get zircon, I want you to put a grid, because I'm looking for zonation in my zircons. You could say segment size. If my segment is more than 20 microns, I'm a little worried about that, so I want to put a grid inside that segment. You can also say if it meets a certain backscatter range. So if you're particularly looking for, let's say, gold-bearing particles, and you want to have a really fine segmentation, if you see something with gold in it, then you can say, if it's bright, we're going to put it over it. Or you can say, I want you to do it for every segment where whenever my point sees cadmium or sees something that we'll further segment that segment, right? So it's elemental triggers. And then hypermap mapping has none of this logic. Hypermap mapping, the idea behind hypermap is that we're not going to bias our measurement at all. We're just going to collect all of the data, and then we can decide what to do with it later. We can segment it later. We can subtract the background later. So it's a much faster way of mapping, because there's no decisions and no image taken. So the image itself. So what we're taking, actually, the BSE image will be at the same resolution as the step size. This is a very fast way of mapping, but your BSE image is at the same resolution as your data collection. So this is kind of traditional QuimScan mapping, right? But we like it. We leave it in. It's great. So every data set is a complex data set. These are multimodal data sets referenced in the specimen coordinate space. And so you're getting your BSE base layer, and we actually now collect more than just the BSE. We could collect 2 channel images at the same time, right? So you can do BSE and CL, for example, or BSE and secondary electron at the same time. And the system doesn't really care what the primary or secondary image is. You can select that in the software to say, which is it? It calls it BSE, but it's primary image, secondary image. You have the segmentation layer, which contains all of the BSE, that should actually say contains the BSE segmentation, and then also X-ray points. This is a binary. Both of these are binary, and that they're binary is really important, because what that binary means is that our data sets are not tens of gigabytes, but are average in the megabytes range, 50, 60 megabytes, as opposed to many gigabytes. We do also have the option to export this data into a raw SQL file, which is not compressed in binary, so that you have complete access to it. And we have a Python package that lets you access this binary files directly, so that you don't have to do that export step. You can just write any sort of algorithm you want, and that Python program allows you to write back to the file as well. Okay, so how does the classification work? AMICS has a couple of ways of implementing classification. First, we have and you can set these up to go in any order you want. And so 1, 2, and 3 here are kind of like the default workflow, but we'll talk about how you can get it even more complex in just a moment. So the first is that you can specify the matching algorithm, and we use a whole spectrum best match at this point. Then it has 3 different priorities, 3 different hierarchical matching. We'll show a diagram of that in just a moment. And then we can do spectrum tree steps and then follow it, and then finally data touch-up steps. So getting rid of some bad data if you want to. So best match classification is, it compares a match of the unknown spectrum to all reference spectra and calculates the closest and best match. And then if it passes your quality threshold, it will match to that. If it doesn't, it will remain unknown. And so doing a match to all reference spectra in the library allows you to make sure that you're not just getting the first match that it comes to, but the best match, and you can have close-face differentiation with that. Hierarchical classification allows you to have different quality thresholds for different spectra or different reference material. So high, for instance, you can go to the high and you can have a very tight numbers on that. Those are the ones you're most interested in. You want to make sure that they're correct and that you're having no false positives. Then if it matches in the high, nothing in a lower category can steal from it, so to speak. And then finally, the spectrum tree. The spectrum tree is a rules-based classification system, so it's a little bit different than matching. And honestly, this is like how I do, I would say 70% of my classification is through spectrum tree, and because I'm usually trying to solve very specific problems. So this is an example where we're actually pulling out organic matter, and we're trying to also segregate whether it's high sulfur or low sulfur organic matter. And so you can see we start with all spectra. We then do a segmentation based on the BSE, and anything that's not organic matter or not BSE, we're going to send over for best match matching. Then we go up to low C versus high C, and then so that's an elemental split, and then we send everything that's low C for spectral matching. And then finally we have the high carbon, and then we split it based on its sulfur content. So this is just one example. We have many different options. There's 7 different things you can split on, including just doing a principal component analysis. And so it can be a great way if you're starting from scratch to figure out what's in your samples. And then finally, I'm going to go through data exploration and watch this space because this is evolving very quickly. We have the ability to extract textual information. And so this is one of the core things that AMICS does, is that you've got the information from the false colored maps, but then it can pick out grains, which are contiguous areas of the same. I know all the geologists are going to go, great, but yeah. So contiguous areas of the same material, and particles, which are completely surrounded by, so kind of the old definition was completely surrounded by background. We've now implemented something that we call de-agglomeration, which tries to separate out touching particles based on grain shape and some mathematics around that. That's definitely an evolving area, and maybe a place where machine learning can be very valuable. So we're going to have some examples in this section. So large area mapping. This is a gigantic map that we collected, and so the square is 4 millimeters on a side there. So you can see this is over a very large area. This was actually collected to try to see how big of a data set we could collect, and it was what was it, 6 gigabytes, Patrick? 6 gigabytes. Yeah. So that's our largest file to date. This right here was a hypermap test, and so this is it has BSE, classified layer, and the UVD layer. Black mass data, so particle data from crushed black mass. A mineral processing example. That one was collected just by taking tape and pressing it into the foam at the top of the mineral processing vat, which is pretty cool. Particle grids, chalcopyrite and pyrite. Sort those particle grids by bin. I told you're going to get one reservoir slide. So this is it. No, you won't have too much pain after this. These are all thin sections. and we can apply weight percent and area percent for each of the different phases. An iron ore example. This is from a Neoproterozoic iron ore, banded iron formation. Very cool. And we're using spectrometry here to separate out magnetite from hematite. And so we can separate that out on multiple criteria to have a high confidence separation. Slag. So this is another important point, is that we can apply quantifications directly in the software. And so in this particular case, we're going right to a spree, right? And so it doesn't do the quantifications in AMICS itself. And instead what it does is it points itself towards another quantification engine, right? And so this is another place where we have the possibility to, if someone requests some development, we could connect to any quantification engine, because what we're doing is we're using an API to send the spectra for quantification and bring it back. So that's how we get this elemental. So you're not seeing the theoretical values based on the material definition, and instead what you're seeing is quantified results. And so you're setting up the method someplace else. And the main thing that this is doing is, in this particular case, it's been set up to combine the spectra into a sum spectra based on the grain that's been identified. So this is used for indicator mineral quantification, for example, and you can see an example here where we're quantifying the X-rays here by sending it to a third party. This is slag, large area mapping, 5 millimeters by 15 millimeters. So again, a nice big sample, which is cool. I love this one. This is small particles in steel, and quantifying what those particles are over large areas, and the shape analysis from those. Comparing two different steels and the data from two different steels. This was used for identifying the source of that cleanliness issues. Looking at different types of precipitates and steels. And pore shape classification and extraction. We also have the ability to do a lot of stuff with the particles and being able to export those particle images. So we've got a lot of people looking at machine learning classification of particles right now, where they use AMICS to first filter the data set and then export the particle images into be able to classify them. So a point I've made a couple of times here, but we're really customer-led development. So our development team, we have, right now we have 2 full-time developers working on AMICS. We have an applications team from around the world, but we are focused on, our work is really focused on making sure that we're meeting our customer needs. So when we have requests, we have a backlog. You can report bugs directly to us. Bugs do happen. Like I'm a development guy, not a sales guy, so I'm going to tell you the reality is, we are working fast and breaking things, but one of the important things is that we try to address those directly. We give you direct access to the development team, and we make sure that when we are adding features that we're listening to our community feedback. We do user group meetings. I think our next big meeting with users is going to be in Australia, but we do hope to have one in the East Coast of the United States sometime around spring break at West Virginia University, so who has agreed to host it. So we also have a stable of consultants around the world, so if you're looking for method development assistance, we have that available as well. Thank you guys so much.